Good afternoon, dear friends. For your attention, the following lecture of the topic Distributed Element Circuits. This lecture is devoted to the very interesting question of the velocity and which voltage and current waves propagate in a line. In this lecture, we will recall the features of the wave propagation process, introduce the concept of phase velocity, and investigate phase velocity and real power transmission lines. We will find out if the phase speed can exceed the speed of light. I will leave this question unanswered for now, but you will know the answer at the end of the lecture. And as always, we will conclude this lecture. So, let's start. In the previous lecture, we found out that two independent wave processes operate in a line with distributed parameters, direct and reverse waves. A direct wave propagates from the source of energy from the beginning of the line, and its amplitude decreases with increasing distance from the beginning. On the contrary, the amplitude of the reverse wave increases. The further we are from the beginning of the line, the greater its amplitude. The current and voltage at any point on the line are the algebraic sum of direct and reverse wave. This superposition of direct and reverse wave leads to the fact that the total voltage or current at some points of the line may exceed the supply voltage or current. A direct wave carries energy from the power source to the load, which is connected at the end of the line. And the energy of reverse wave spreads from the end of the line to its beginning. That is, in this case, not all the energy of a direct wave falls in the load, but only a part of it. This reduces the efficiency of the line. Wave impedance is the coefficient of proportionality between the voltage and current of direct and reverse waves. This is the physical meaning of wave impedance. However, in the previous lecture, we didn't say anything about the speed with which these waves propagate along the line. This will be the subject of our lecture. As we have just said, the voltage and current at each point of the line is a superposition of the two types of waves propagating in this line. A direct wave spreads from the beginning of the line towards its end. When this wave reaches the end of the line in which the load is connected, its spatial reflection occurs. The wave seems to be reflected from the end of the line and begins to move in the opposite direction to the beginning of this line. These processes can be understood in more detail by looking at this picture. In this picture, the direct wave is shown as a solid line, and the opposite reflected reverse wave is shown as a dotted line. From the this picture, you can see that the waves in the line propagates at a certain speed. It is intuitively clear that the speed of wave propagation can be determined by setting a specific point and tracking the movement of this point along the line. As such a characteristic point, you can take, for example, the maximum of the oscillations of its 0 point. But let's remember that the wave process is a damped sine wave, and a certain point of the sine wave is determined by a certain value of its phase. Thus, we arrive at the concept of a phase velocity of the wave. The phase velocity can be imagined very simply. Let an observer somehow fix a certain phase of oscillation of a direct wave in a line with distributed parameters. But this oscillation, as we can see in this picture, doesn't stand still, but moves from the beginning of the line to its end. To see the phase of oscillation constant all the time, he needs to move along the line with some speed, as shown in this picture. Let the observer fix the phase which is marked in the picture with a red dot. This dot with a certain phase, as we can see, doesn't stand still but moves. To track it, the observer himself must move at the same speed in the same direction. That is, we can say that the phase velocity of the oscillation is equal to speed of the observer who moves along the line and observes the same phase of the oscillation. Here it's especially necessary to pay attention to the fact that the speed of movement of observer is only equal to the phase velocity, but it is not the phase of speed itself. This is very important because the observer is a material object, but the phase of the oscillation, unlike observer, is immaterial. We will return to this fact when we talk about the maximum possible phase velocity of the oscillation in the line. Let's try to calculate this velocity. To do this, remember that the phase of the oscillation is called the argument of the sinusoidal function that describes this oscillation. For example, for the voltage of the direct wave, which is described, as we remember, by the following formula, the phase is the expression in brackets. That is product of omega by time t, the initial phase of the direct wave, and the product of the phase factor beta by the distance x. A constant phase of the wave corresponds to a certain constant value of the sinusoid. The base of the calculation will be to define the phase velocity as propagation velocity of the phase of the oscillation with some constant value. Let us recall, for example, the equation for a direct wave in a line. It is known from the previous lecture that the direct wave is described by the following equation. The phase of this oscillation, that is the argument of the sign according to the definition of the phase velocity, must remain unchanged. That is, we can write the following equation. Let's find the time derivative of this expression. This derivative is presented here. This derivative is zero because, by convention, the oscillation phase is constant. Note that the phase can have any value, but this value doesn't change over time. And the derivative of a constant value is zero. In this formula, the derivative dx concerning dt is the phase velocity. Denoting this derivative as Vf, we get that the differences between omega and the product of Vf and beta is zero. From here, it can be finally obtained that the phase velocity is directly proportional to the oscillation frequency and inversely proportional to the phase factor beta. This is a very important conclusion which will future help us to understand what was the reason that the telegraph cable between Europe and America, which we talked about in the first lecture, worked with very large distortions. Now that we know how to calculate the phase velocity of waves in line with distributed parameters, let's determine a real value of the phase velocity in real power transmission lines. To determine the phase velocity of waves in real power transmission lines, the characteristics of power transmission lines in southern Ukraine were taken. The research was carried out at the Department of Electromechanical Engineering of Odessa Polytechnic National University and presented at the International Scientific Conference, the name of which you can see here. You can read the research results in detail in the article at this link. All initial and estimated data are summarized in the table you see on this slide. In this table, for each line, its primary parameters, the calculated values of the secondary parameters, wave impedance and propagation coefficient, propagation factor, and the calculated value of phase velocity are given. In all cases, 340 radians per second are taken as the angular frequency omega, which corresponds to the industrial frequency of 50 Hz. Note the phase velocity values which are given in kilometers per second. For all lines, the phase velocity exceeds the speed of light, which is known to be 300,000 kilometers per second. But physics teach that the speed of light is the maximum in nature, and nothing can not only move faster than light, but even reach it. Maybe there is an error somewhere. Please check the calculations. You already know all the formulas from the previous lectures, and the primary parameters of the lines are given in the table. As you can guess, there are no errors here, and the fact that the phase velocity exceeds the speed of light can be explained. We will explain this on the next slide. First of all, let's remember that modern physics forbids material objects to travel faster than light and to transfer energy and information faster than light. Let's figure out whether the phase of oscillation, we are talking about the speed of movement of a constant phase, is related to these concepts. First of all, the oscillation phase is not a material object. It's just an ordinary number, the argument of a sinusoidal function. That is, from this point of view, there is no prohibition on exceeding the speed of light. Secondly, when we talk about phase velocity, we mean the speed of movement of an unchanging phase state of a certain wave consisting of only one oscillatory process. For example, earlier we talked only about the direct voltage wave, but the voltage wave itself cannot carry electromagnetic energy. Remember, energy, and with it power, occurs when voltage and current act simultaneously in a circuit. After all, the instantaneous power is the product of instantaneous values of voltage and current. If there is no thing, either current or voltage, then there is no energy. That is, a single voltage wave or single current wave cannot carry electromagnetic energy. From an energy point of view, there is also no prohibition to exceeding the speed of light. And third, a sine wave of constant frequency cannot carry information. After all, the law of its change remains the same over an infinitely long period. Thus, from the point of view of modern physics, there are no restrictions on the magnitude of the phase velocity. But to transmit energy or information, we need to have several waves of different frequencies, which superimposed in each other would form a non-sinusoidal oscillation. That is, no transfer energy or information you need to transfer energy or information you need to have so-called wave packet of several waves of different frequencies. The movement of such a wave packet is shown in this figure. In this figure, the red square marks the constant phase of oscillation, and the green dots mark the beginning and end of the wave packet. Look closely. The red dot is moving much faster than a wave packet itself. The speed of the wave packet was called group speed. The group speed, or group velocity, unlike the phase velocity, cannot exceed the speed of light. Thus, the phase velocity of waves in a line with distributed parameters can exceed the speed of light. Our lecture has come to an end. Let's summarize what we learned. Firstly, waves in lines with distributed parameters propagate with a certain speed. There are two wave speeds, phase velocity and group velocity. Phase velocity is the speed of propagation along the wave a certain phase of the oscillation. Waves of different frequencies have different phase velocities. The higher the frequency, the greater the phase velocity. The phase velocity can exceed the speed of light because the phase of the oscillation is not a physical object. Group velocity is the speed of movement of a set of waves of different frequencies, so-called wave packet. It is these wave packets that can transmit information. The group velocity is always less than the speed of light. Dear friends, thank you for your attention. Have a nice day. Goodbye.